Year 11. Today what we're doing is looking at logarithmic functions. So what we're going to do is look at what a logarithmic function looks like graphically. We have investigated them algebraically, but now we're going to look at how to graph them. So a logarithmic function is a function in the form of y equals log base a of x. And the logarithmic function y equals log base a of x is the inverse function of an exponential function y equals a to x. This is because their graphs are reflections of each other in the line of y equals x. What we're going to do for our first example is we're going to sketch the graph of y equals x, y equals 2 to the x, and y equals log base 2 to the x. So you're going to want two different color pens. I've already sketched y equals x for you in pink, so try and pick two different colors for me. Now, if we're looking at y equals 2 to the x, what we want to do for that is we want to say that this is an exponential function, meaning that it is exponentially increasing. We know that it's going to have an asymptote at our x-intercept as well. What we're going to do is we're going to substitute in values into our calculator, x values, to get y values that we can plot, and then we can sketch. So if I substitute in -1, so 2 to the power of -1, I get that that is equal to a half. So that's my first value there. Then if I substitute in 2 to the power of 0, I get my answer is 1. If I substitute in the value of x equals 1, I get 2. The value of x equals 2, 2 to the power of 2 is 4. And 2 to the power of 3 is 8. Now, if we used to do 2 to the power of 4, that goes off our graph and is actually 16. So what we can now do is we can sketch our graph going smoothly through our points like so, and showing that it's exponentially increasing. We're going to put our coordinates at all of those points. We're going to write them on. The reason why we're going to write them on is because we have inverse function. So with our inverse function, what we have is that this means that our exponential is going to be reflected in the line y equals x to get our logarithmic function. So what we have is we have that when we want to find this, we have that y equals 2 to the power of x has an asymptote at at y equals 0, which is at our x-axis. Now, with inverse functions, what we do is we swap the variables. So, or swap the values of x and y. So, inverse functions, we swap variables. And if you do extension, you would already know this. If you don't do extension, don't stress too much. It's just to show you what's happening. So, if we swap our variables, and what we will have is we'll have, instead of y equals, we're going to have x equals 2 to the power of y. What we then want to do is we want to make y the subject by using our fact of our log BAP, where we have our base power equals our answer. So if we do that, we know that our base is, in this case, 2. We have, our power is what it equals. So our power is our power, so our power is y, and then our answer is x. So if we were to write the exponential that we have swapped the variables to find the inverse function in our logarithmic form, what we'll get is log of our base of 2 of our answer of x is equal to y, which is our y equals log base 2 of x. which is the function that we've been asked to draw. So this just shows, and proves to you that we have inverse functions between our exponential and our logarithm. So what this means is that to sketch y equals log base 2 of x, we're going to swap all of the values of our coordinates, meaning that my original value of -1/2 is going to become, we're going to swap the coordinates to become, my pen, 1/2 minus 1. Then we have the coordinate 0, 1. It's going to become 1, 0. We have the coordinate 1, 2. It's going to become 2, 1. Then we have our coordinate 2, 4, and 3, 8. They are going to become, oops, that's a very bad arrow. They are going to become 4, 2, and 8, 3. These coordinates are now all coordinates that fit on our logarithm. So if we go to 1/2 minus 1, then we have 1, 0, 2, 1, 3, 2, 1, 4, 2, and then 8, 3 would be our next one, which is off the graph. We can now draw our logarithmic function, and we can see how it is the inverse of y equals 2 to the power of x. We can see those coordinates and how they have flipped. Oops, whoa. And 1/2 minus 1. And we can see how they have flipped. That is then our graph of y equals log base 2 of x. And our blue graph was y equals 2 to the power of x. Now, what we'll notice is that y equals log base 2x has an asymptote. Instead of y equals 0, like we had for our exponential, it's at x equals 0. And so this is for any logarithmic function, apart from those that have been manipulated, they have an asymptote on our y-axis where x equals 0. So that's a quick way to sketch our logarithmic function. What we can also do is we can just substitute in x values into our logarithmic function using our calculator, creating a table of values. The next example, we're going to sketch the graph of y equals x, which I've already done for you, and y equals e to the x minus 1, and y equals log base e x minus 1. So if we look at our first one, y equals e to the x minus 1, it's translated. What we have is it translates, or we're looking at our parent function, y equals e to the x, 1 unit down. Okay, in order to sketch this, what I'm going to do is I'm just going to put in some values into my calculator. Oops. So, my first value that I'm going to put in is 0. So if I put in my calculator, shift e to the power of 0 minus 1, I get that my x-intercept is my y-intercept, which is at 0. I'm then just going to substitute in a value for 1. So when I substitute in 1, I get that it is at 1.7. Then when I substitute in 2, I get that that is at 6.39. When I substitute in 3, I get that that's at 19, which is off my graph. Now I'm just going to see what happens on the left-hand side of my y-axis. So I'm going to substitute in a negative. So if I substitute in -1, I get negative 0.6 to one decimal place. And if I substitute in -2, I get -0.8. So what we see is that it has a asymptote. If it has an asymptote, sorry, my pen. So y equals e to the power of x minus 1 has an asymptote at y equals -1, because normally the asymptote for an exponential is at y equals 0. So we're going to draw our asymptote on before then sketching our exponential function. And so that was the point 1, 1.7. That was the point 2, I think it was 6.4 to 1 decimal place. Okay, and that is our graph y equals e to the x minus 1. Now with our next graph, which is our y equals log base e x minus 1, what happens is it translates y equals log base e of x 1 unit down as well. So what we're going to have is we can also rewrite this, as because we have log base e of x, we can also write this as ln x minus 1. They're the same graph. Because we're not moving it left or right, our asymptote will still be at the same asymptote for any other log, which is at x equals 0. So we're going to have an asymptote along our y-axis. So what we just have is that it's moving down 1. What I'm going to do is I'm just going to put in x values into my calculator. Now, if I do ln of -1 minus 1, I'm going to get a math error because my log function does not exist on the left-hand side of my y-axis because of my asymptote at x equals 0. So then if I substitute in ln 0, again, it doesn't work because that's where my asymptote occurs. But when I sub in ln a half, what I get is at ln a half, I get -1.69. So that's about there. Okay. When I substitute in 1, I get that it's at -1. When I substitute in 2, I get that that's at -0.3. When I substitute in 3, it's just above my x-axis at 0.09. And when I substitute in 4, it's at 0.38. So my logarithmic function is like so. What I'm going to do is I'm going to make sure that I label some of these points to show that I have an understanding of them. I'm going to do just a few of them. Like so. Now, because we have some movement in these two, it means that they're not exactly going to be, because we have the translation, it means that they are not directly inverse functions of each other around the line y equals x. Okay. What we're going to do is turn to the next page. On our next page, we now want to sketch the graph of y equals 3 log base 10 of x plus 4. So I've just included the line y equals x just for fun. Just ignore it. What we have is we're sketching our log, so y equals 3 log base 10 of x plus 4. Okay, we're not shifting the graph to the left or the right. If I try in my calculator and I go 3 log base 10 of 0 plus 4, I still get an asymptote at my x equals 0. So I still have the asymptote on my y-axis and my function is to the right of my y-axis is where it's going to occur. What I'm going to do is I'm going to substitute in some values. So I'm going to start with 0.5. So when I substitute in 0.5, I get just above 3. I get 3.09. When I substitute in 1, I get that it is at 4. That's because my graph has been translated up 4 units. When I substitute in x equals 2, I get 4.9, so just below 5. When I substitute in 3, I get 5.4, so just above 5. And when I substitute in 4, I get 5.8, so just below 6. So what we have is we have our exponential function, our logarithmic function looking like so. We want to make sure that we label a key point, so the 0.41, we want to make sure that we include the label of the function. We want to include our arrows as well. So pretty much to draw a logarithmic function, you need to know where the asymptote is, and then you just plug in x values into your calculator to graph it, and you make sure that you label one of those key points. And I've just realized that this is the 0.14, not 41. Hopefully one of you figured that I wrote that down wrong. The last thing I need to talk to you about is logarithmic scales. So it is difficult to describe and graph exponential functions because their y values increase so quickly. We use logarithms and logarithmic scales to solve this problem. On base 10 logarithmic scale, an axis or number line has units that don't increase by 1, but by powers of 10. Example of base 10 logarithmic scales are the Richter scale for measuring earthquake magnitude, the pH scale for measuring acidity in chemistry, the decibel scale for measuring loudness, the octave scale, which is the frequency scale in music. What we're going to do is we're going to look at pH in the first example. So Jed finds that the pH of soil is 4 in the eastern area of his garden and 6 in the western area. The pH formula is logarithmic and pH less than 7 is acidic. We want to know what is the difference in acidity in these two areas of the gardens. So what we start off with is we do our difference in pH is equal to our two different pH levels, which is 6 in the western area and 4 in the eastern area. So 6 minus 4 equals 2. Then we use our logarithmic scale. And with our logarithmic scale, what we do is we start at, our logarithmic scale is y equals 10 to the power of the difference. So our difference in our pH is equal to 2. So that means we're going to have y equals 10 to the power of 2, which is equal to 100. So what this means is therefore the logarithmic difference in acidity is 10 to the power of 2, which equals 100. This means that the lower the pH, the more acidic. So the soil in the eastern garden, is 100 times more acidic than the soil in the western garden. Okay, if Jed finds another area with pH of 3.6, how much more acidic is this area than the eastern area? So again, we have to work out our difference in pH is equal to our eastern area was 4 minus our 3.6 of the other area is 0.4. So therefore our logarithmic difference in acidity is 10 to the power of 0.4. So it's 10 to the power of our difference is what we did. 10 to the power of our difference, which is equal to 2.51188. Okay, which equals 2.5 if we do it to 1 dp. So therefore, actually, I might write that on the next line. Equals 2.51 dp. So therefore, the soil in the new area is 2.5 times more acidic than the eastern area.